AP stats. Sorry about that. On the previous podcast, I accidentally flashed grades up there because it was another screen. So obviously can't include that in the podcast, can we now? My apology on that. I did want to go ahead and just kind of give to you the concept list. This is on the same topics page that we just came from. It should actually be right above where I'm talking here. But I wanted to just kind of start off by going through a couple of concepts, just kind of addressing what each of these represents and what I'm talking about when I say, hey, area and a normal distribution. What does that even mean? What does it mean to say a probability distribution? What does that even look like? What do I need to know about it? And all of that sort of thing. So as you go through each of your review sessions, I would always kind of come back to this podcast because this would be a good one of just saying, hey, these are the main concepts you need to know, right? So again, very important as we're thinking of, oh yeah, what do I need to remember again? Like what specific things? The podcast below this one kind of goes into specific questions, specific problems. This one goes over overarching themes that are on the final exam. And so that would be something that you might want to just take a look at. As we start at the top, let's go over the different FRQs here. The first one being finding the area between two values in a normal distribution. The random table, random digits, talking through that process. Well, let's say that we label everyone in our class from 01 to 32, okay? And we decide that we're going to randomly select 10 people to exempt the final, okay? It's important that you understand that we label, right? That I say that each person gets a number between 01 to 32, right? So we label from 01 to 32. Now, once I label that, my next part is to be able to say, okay, what do I do from labeling? Now, I'm going to choose, right? So I'm going to choose 10 people without replacement. And we would ignore the repeats, right? We'd ignore repeats or numbers outside my range, okay? So knowing how to not only describe how to do the process, but also carry it out. So after I would say that, okay, I choose 10 people without replacement, ignore repeats, numbers outside of my range, and that maybe put a little context in here, I would then execute it. So then maybe I have the random digits of, I just made this up, by the way. They'll give this to you. They'll then say, carry out this scenario by choosing the first 10 numbers. So 97 would be outside my range. 15 would actually be okay. 77's outside my range. 62, 31's in my range. And so 15 and 31 would be the only two that we would have within the context of the random digits that I randomly created or just dreamt of. And so being able to show that on an FRQ is very important, but really being able to describe it. So make sure you go over that there. Also, finding the area between two normal distributions or two values. So if I have, this is a normal distribution where we have our mean and our standard deviation, knowing, let's say the mean was 70, if I say what's the probability of getting something between 55 and 80, we would know that 55 would be here, 80 would be about right here, and then we would just find the area that's in between, right? And we could use normal CDF. Again, I'm going over a lot of stuff here, but this would be lower, comma, upper. Make sure you write this out on an FRQ, comma, mean, comma, standard deviation, right? And then plug in the actual values that's here. So make sure you know how to do that. Use the table of random digits, use graph to figure out which represents the specific situation. Yeah, so being able to kind of use the graph to see which graph would represent my situation, my simulation that's there, okay? Make sure you give evidence on why, all right, being able to talk it through. We then use this to find expected value. Whenever I see expected value, I think mean. Remember, when we talked about an expected value, let's talk about a probability distribution, which I think is down below somewhere. But let's say we have an x and probability of x value. The x values are the different values that could be taken. So 0, 1, 2, 3, and 4. And the probability is associated to each of these numbers. So maybe this is 0.3, maybe this is 0.2, 0.3 again, 0.1, and 0.1. The expected value would be the values of x and the probability multiplied together and then added from there. And make sure you show that. So my expected value equals 0 times 0.3 plus 1 times 0.2, and then I would just keep going, right? To be able to show that there. So that's FRQ1, the different concepts from that. FRQ2 is using find the expected cost. Man, this might be a good one. I might have to actually look at that one. If you remind me on the live podcast when I do that later on this week, just remind me on this one. The key that I think we're looking at is, remember the copier one, where we take the copier and we say the expected value from that one. It was the chapter 6 test. I think it's the first FRQ. Look at that one. That's a really good example of number 2 of what we're looking for on that one. Know how to draw a box and whisker plot. A couple things on the box and whisker. Make sure that if I'm putting a box and whisker here, right? And maybe another one's like right here. I'm just making this up, okay? It's possible to have outliers on the outside, okay? So that's a couple things. First off, we have to check for outliers, right? The outlier formula, and this is not on your formula sheet, so you want to get this down. It would end up being Q1 minus 1.5 times IQR, right? And this is Q3 minus Q1, right? The higher end, so this is the lower end. Anything that goes lower than this is an outlier, right? And anything that goes higher than Q3 plus 1.5 times IQR would be an outlier here as well, okay? And that's why you would have an asterisk, and then the next highest value would get the whisker. Now, this right here is my minimum value. This is my Q1 value, the 25th percentile. This is my median, or the Q2, or 50 percentile. Q3 would be the 75th percentile, and then my max is out here with outliers on this outside. So just again, identify how I create box and whiskers, and then also remember that below you want to put context to the left and to the right. Maybe you label A and B here, but with context, we're talking about the number of free throws from the teams in our region or something. I don't know. So something like that. And then be able to talk about socks. That's a big thing too. When I say describe the box and whisker, talk about my shape. How does the shape compare, right? And don't say, here's this one, here's this one. No, talk about how when looking at both shapes, both appear approximately normal, right? Or one looks skewed left compared to the other one skewed right. Talk about the center. Talk about the spread. Talk about outliers if there are any. Okay? Talk about it in a context. All right, number 4, we just talked about an area in a normal distribution. Make sure you know how to do that. Make sure you know how to do this both with if I'm finding this area, right? Here's my mean, and I'm looking here. Know how to find that using normal CDF. Also, make sure that you know how to use a z-score, that it's my value minus my mean divided by my standard deviation, right? Remember that in the context of chapter 7.2, we looked at our final thing where we said our z-score is the value was p hat, the mean was P, or my true proportion of my population, and my standard deviation was the square root of P times 1 minus P divided by N. Okay, so make sure you know how to do that, where the P is from my proportion population. Remember statistic and, I'm going all over, but remember statistic and a parameter, the difference there. Number 5, independence and probability distribution. All right, so remember independence. Couple things with independence. If they tell me probability of A is 0.25 and probability of B is 0.36, and they say, what is the probability of A and B? Remember, by definition, I'll put it in a different color here. By definition, independence, if it is independent, this is equal to the probability of A times the probability of B. Now, if it was dependent, put dependent down here, then what we would say is the probability of A is multiplied by the probability of B, given that A occurred, right? Because A is dependent, or I'm sorry, B is dependent on what happened in A. So this is the difference. So on this one, up above, if it was independent, we simply multiply them, right? 0.25 times 0.36. Down below, we would actually have to have what is this, right? We have to figure this out when we're solving for that. But this is the definition of independence. Again, it is not on your formula sheet. You will need to know that. So just remember that as you're studying. The slope of the least squared regression line, I saw this a lot on number 6. On number 6, let's say we have y hat is equal to 3.5x plus 3, okay? Couple things on this. We recognize that this is my slope, and this is my y-intercept. Now, with the y-intercept, if you remember from algebra, has a point of 0, 3, which means that if x is 0, whatever the context of that is, right? If my height is 0 or whatever, then we could predict that y hat would be 3, right? Because y hat means predicted value. Remember, an LSRL comes from this idea of having a dot plot and having a line that represents and goes through it that minimizes the residuals, right? Minimize the residuals, and residuals is just a fancy word for error, which is the distance from each of these points to the line. Okay, minimize residuals. We also represent that the slope, if it's 3.5, means it's rise of 3.5 over run of 1. So my rise relates to my y, right? Whatever the context of that is. And the 1 relates to x. So let's say that we're talking about, I don't know, GPA and hours studied, where x is the explanatory. We'll say x is GPA, and y is hours studied. I don't even think this makes sense, but just go with it. So what we would say is explains the hours studied, okay? And what we would say is, as 3.5 hours studied increases, GPA increases by 1, right? So it's rise over run. So just again, that's how we would describe the slope of a LSRL. Number 7, sampling distribution is a sample of a sample. Remember when we talk about mu of p hat, or standard deviation of p hat, we remember that the formulas are p and square root of, and this is on your formula sheet, by the way, this is square root of p times 1 minus p over n. Make sure we remember that. The probability and normal distribution, if I say what's the probability of, I don't know, something like, let's say we have a mean of 2.4, standard deviation of 1. So if this is 2.4 and I say what is the probability of getting a 5 or higher, probability in normal distribution is, this is all 100%. So from 5 to the right, this area is probability. So let's say you do normal CDF, you could do that as well. Another idea that you need to know is if I were to, coming back to this in yellow, if I were to say the area is 0.1, and they give you maybe this information, and they say, what is this value? This is where you can use z-score and actually go backwards, right? We could go backwards with this. But if they give you the area only to have you find the actual value, remember that you have to go to the left, right? To the left in that. And you would use inverse norm, which is the opposite of normal CDF. So just again, something as you're studying off that. Number 9, probability of one thing given that another occurred. We just kind of looked at that. That would be the probability of A given that B occurred, right? Remember that this formula, when dependent, is probability of A times the probability of B given that A occurred, right? Does what happened in A impact B? And that's what we're looking at there. Tree diagram to solve a problem. This is one, you could go back to chapter 5 here with the tree diagram stuff. So this is a chapter 5 problem. What this talks about is, let's say that there's a vaccine that says yes and no. And it says yes 10% of the time and no 90% of the time. And then it says, when it says yes, it is false. We'll say 0.1% of the time. And it says true, or it is true when it says yes 90% of the time. For no, it could either be false or true, right? It is false, let's say, when it says no, let's say it's false 0.05% of the time, and 95% of the time it's true. It then asks, what is the probability that it would actually be false? Like these tests would be false, whether it said yes or no. And this is where you'd have to multiply 0.1 times 0.1, which is 0.01, and 0.9 times 0.05, which is 0.045, right? I think that's right. Yeah. 0.045. Yeah. So you would say that the probability would be this plus this, right? So noting how to create that tree diagram if you have multiple scenarios, and when to use that tree diagram. So that's a big part of it. Venn diagram and probability. Another good one, if I say what is the probability that is either red and yellow, I don't know, whatever we're talking about, is 0.3. The probability of red is 0.4. Probability of yellow is 5, right? So in this example, noting that a Venn diagram might be a good way to help, where the middle here would be 0.3, right? The probability of red, which is the full circle, say this one's red, this full circle is 0.4, but notice that we've got to take away the 0.3 that's included, so there would be 0.1 here. The probability of yellow, this whole thing is 0.5, but we have to subtract 0.3 to get 0.2. And so what we could say is 0.1, 0.3, 0.2, that's all 0.6 if I add it together, which means that it would be neither 40% of the time, or 0.4. So using a Venn diagram is another good way. Numbers 10 and 11 are both from chapters 5 if you're going back over there. A probability distribution, remembering that a probability distribution is where you have values of x and the probability of x, where each value, whatever it is, 1, 10, 11, 12, whatever, has a probability between 0 and 1, and they all add up to be equal to 1. Okay? What's up, Emmy? So we got that on number 12. On number 13, remember a binomial, geometric, and neither, noticing the differences. If you look on chapter 6, number 2 FRQ, that's a really good one to kind of go back to if you're looking at that. Binomial is bins, right? It has, bins, there you are. Set number has a set number of trials, and bits has a trials until success, okay? So that's a good example of something going back to just noticing the differences. Again, that was chapter 6. Estimating the standard deviation by using a graph. They're going to give you something that's a normal distribution. I think there was one off the test, either chapters 1 or 2, where they'll literally give you this. They'll give you this, 120, 90, 80. And they'll say, estimate the standard deviation. And they'll give you, all right, A is 5, B is 10, C is 20, right? D is 30. You're looking for the best answer, like E is none, or I don't know, something like that. As I look at this, you'll notice that the 68, 95, 99.7 rule applies. So this is 1 SD to the left and to the right. This is 2 standard deviations to the left and to the right. And this is 3 standard deviations to the left and the right. So if you looked at 5, for instance, and this is the mean, 5 to the right would be 1, 2, 3, 4. Like this would be 5 standard deviations. It's not even close, right? We would want 3 standard deviations would be the majority of this, right? That's what we're looking for. So you want to try to find something that corresponds to the right proportion as it relates to the graph that they give you. Number 16, double blind. Double blind is where, so a single blind, let's talk about single blind, is where the participant is unaware of the treatment that's been given, right? Again, we're talking experimental world, which, by the way, I'm kind of going off on a tangent here. Experimental has cause and effect, right? So cause and effect, where observational can only show tendencies, right? This would be more like correlation, like this correlates with this, right? So that would be what we're looking for there. So cause and effect can only be experimental, and experimental, the difference is you assign treatment, okay? Sorry if you hear my daughter. We'll keep it rolling. But a single blind experiment is something where the participant is unaware of the treatment group. We do this to overcome the placebo effect. So they don't know what they're being given, okay? Double blind is where the participant and the individual conducting experiment is blind, or they're both blind. The individual conducting experiment are both blind to the treatment. Okay, so that would be double blind. That's the difference between double and single blind there. 17, analyze a box plot and compare. You'll notice, man, there's a lot of these on here. Number 17, y'all. Got to make sure you look at that. The box and whisker plot are huge, making sure you understand what each of these parts mean and knowing how to compare them, right? Which one has the... I think this is one where they're going to give you 2 box plots, and you're going to have to kind of compare, like, based upon the statements in the multiple choice there. So just make sure you go back to that one. Selecting values from a random digit table, ignoring repeats, well, it depends if we ignore repeats or not, right? So if I were to say, draw an ace, I want to simulate draw an ace with replacement, using the table of random digits, I'm just making stuff up, I'm sorry. On this one, you would label the cards from 01 to 52, okay? All right, label them. We would choose, with replacement, I would choose 1, right? Choose 1. And let's say at the beginning they said they'd simulate 10 times, okay? So what I would do is start with this one, and when I label the card 01 to 52, aces would be, let's just say 01 to 03, because that's, I'm sorry, 04. My apology. So then we would go to 24. This would not be, because it's not between 01 to 04, so this would be no ace. Knowing this, right? 86 would be, hold up, make it sure. Okay. I say this, each set of two numbers, right? No ace, or actually this would be outside of my range, right? So this would be no ace, outside range. This would be no ace, no ace, no ace, no ace, and I'm just making one up. That would be an ace, right? But notice that each in this one, because it's replacement, any repeats we would not ignore because each one is separate. So making sure you notice the difference between one that has with replacement, which is an independent event, compared to one where it would be without replacement, that would be a dependent event. And so just notice the difference as you're simulating on the random digit table. Block something in the experiment where we are blocking. Let's say that we are, again, this would be more of an experimental thing. So if I have 20 people, and I say instead of randomly assigning, yeah, you saw what I wrote there. My apology. No, I'm not apologizing, I'm joking. So we're randomly assigning them into two groups where one group goes this way, one group goes this way, right? So we talked about this thought process, right? And once I plug that in, go from there. A block allows me, instead of randomly assigning here, we start with 20 people, and instead of imposing a treatment on one and so on and so forth, before we do that, we actually end up blocking. We put a block in place where we'll put maybe 10 males and 10 females, and then we almost have too many experiments where we'll randomly assign, right? Randomly assign, talking through that. We'll put them into group 1 and group 2, group 1 and group 2. We give them the treatment 1, treatment 2. So this is G1, G2. I'm just giving you a little bit piece of this. Treatment 1, treatment 2. We allow that to go for a certain period of time, and then we compare at the end, right? Compare at the end. So that would be a good example of something where we are blocking, where you're imposing something on the actual experiment and putting people into different groups that might show a different tendency towards the treatment that's been given. So just a heads up there. Finding the slope from the formula. I think we talked about that. Oh yeah. Oh no, actually not. This is so when we look at R times S of Y over S of X, and this equals the B, I think is what it says. Remember that, or maybe it says A. I forget what it says on your formula sheet, but this is the formula where Y hat equals AX plus B. You just got to remember this, okay, y'all? I'm going to give you the standard deviation of Y and the standard deviation of X as it relates to my scatter plot, so out of all the data. And then the R is, if you remember, this is the, so this is the correlation, right? And this shows the strength of the dots. Remember to describe what this would be, we would actually do DOFs, right? Which would be direction, outliers, form, and strength. R is the part that allows me to see the strength of this. So the tighter, the closer this value is to 1. But if it's really spread out, this value is going to actually be closer to 0, right? If it's positive, that means it's going to be in the top right, top left. And if it is negative, put it here, it's going to be falling down, right? But the closer to 1 and negative 1, the stronger it is. We talked about this idea on number 21, the 99th percentile. If I did the 99th percentile, it would be all of these right here, where the area here would be 0.99. You could use a z-score or inverse norm, but this would be the value minus mean divided by standard deviation. Traditionally, they'll give you the standard deviation and mean. They want you to find the value. It's like you're working backwards on this one. But you'll go to table A and find where you have the area of 0.9999, right? And you'll plug that z-score, which is the amount, by the way, z-score, amount of standard deviations above the mean, right? It's not necessarily the area, okay? Make sure of that. It's not like the area inside of it. This is like from here, this might be 2.3 standard deviations above the mean. Or if it was to the left and it was negative, it would be below the mean, okay? So just remember that. You could also use inverse norm here, but just going through all of that as well. Remember standard deviation definition, the average distance from the mean, right? It typically varies by whatever the standard deviation is away from my mean, okay? Number 22, I just told you about that. Make sure you know how to do this, y'all. Value minus mean divided by standard deviation. Know how to use table A. Got to know how to do that, okay? Maybe they'll ask for the mean on that one. So you can't use inverse norm on this if you are given the value, the standard deviation, and the z-score. You might have to work backwards, and so that's why you need to know what each of those concepts are. That's a huge part of this exam is number 22. When do you use mean and median? Remember, if it is perfectly symmetric, my mean is equal to my median, which is why we use our mean. But if it's skewed to the right, the mean is pulled by, it's not resistant to outliers, right? It's pulled by the outliers, but the median usually follows closer to the hump, right? So closer to the left side on a skewed right graph, where mean would be here, right? And if it was flipped, it would be flipped there. So median is what we used on skewed data. So we use this on skewed data, okay? Yeah, number 24, combining two normal distributions, then finding a new normal distribution, and then finding the probability. Here's an example. If I were to give you the information that I've got two normal distributions with, let's say this is how I did on my first part of the multiple choice section of the test, and let's say I got an 80 on this. I'm sorry, let's do this. Let's make it more realistic. A 40 with a standard deviation of 2.2. And over here we got a 50 with a standard deviation of 3.1. And I were to say, what was my overall score? Well, to create my overall score, we'll have a new normal distribution. But in order to add these two together, if I subtract, just kind of note that as well. If I were to add them together, I could just simply add the means, right? Because it's mu of x, which we'll say this one's x and this one's y, plus mu of y. So this would be 90. But one cannot simply add standard deviations, so this is where I would take the square root of 2.2 squared plus 3.1 squared, and that would be my new standard deviation, right? So this would be my new standard deviation. And then it asks, find the probability that if this was the mean for the multiple choice and the FRQs, what is the probability that the combined score would be between 70 and 75? And this is where from here you would have your mean be 90 and maybe 70 to 75 would be this area. And this is where I would use normal CDF. Lower bound would be 70, upper bound would be 75, mean is 90, and the new standard deviation, which would be here, would be what I would plug in. Okay, that is a tough one on that one. Independence and mutually exclusive. Remember, mutually exclusive means that, okay, so independence means that probability of A times probability of B is probability of A and B. The idea with mutually exclusive means that this is actually 0, because what that means is these cannot occur at the same time. And so remembering the difference between these two definitions, independence versus mutually exclusive. All right. Again, some of these I can hit on more. I just wanted to give you an idea. A stem plot, analyze the shape. Observational, experimental, I did that. Geometric formula. All right, geometric formula. Geometric is trials until my first success. So the mean of geometric would be 1 over P. So if the probability is hitting 80%, I'm a 80% free throw shooter, to find the expected amount of free throws I should hit before hitting my first, it would be 1 over 0.8. And then going from there, I think that would be 1.2 free throws expected. Stem plot. If you remember a stem plot's where you have the stem and you have your leaf. Or this would be like, if I was to do this, right? Yeah, 4, 5, 6, and then like analyzing the shape on this. Be careful, because if it flips the other way, you have to almost look at it. You have to look at it backwards. Sometimes I think there were some people that got confused because sometimes there were leaves going this way and then this way. So just make sure you identify, like when you're comparing, how that looks, like which one's skewed, and kind of really focus and look at it, because this one is mirrored on the left hand side. Talking about different types of bias, right? So convenience, or if someone doesn't respond, non-response bias. I'm trying to think of all of them. If you look at around the room, you'll notice that I think it's over by the black wall there, that there's should be some piece of paper over there or around the room that should help you with those different forms of bias. Median definition, this is the 50th percentile. Residual distance is y minus y hat, okay? So I take my actual minus my predicted, and so making sure that making sure that I actually got that definition right. I think it's y hat minus. Oh, no, it's because the predicted, so the actual, like these dots, right here. This is like my real y. This is like my y hat. Y minus y hat, this is called my residual distance. And where I minimize the residuals of a scatter plot, it creates my LSRL, my least squared regression line. Because think about it, my least squared regression line. Okay, so again, just an example of that. Mean and standard deviation, know how to combine. I kind of went through that beforehand. And z-scores, finding the z-scores. How do I know who did better? Well, it depends. If they have two different tests, whoever has the highest z-score is in the highest percentile, which allows me to say this person did better than this person. So z-scores, y'all, a big concept on there. Z-scores, I see a lot of box and whisker plot. I see a lot of least squared regression line, like slope and definitions along that there. Again, just going through that. You'll have an hour and a half to take this. It is twice the normal test that's there. So again, do the best you can in doing those out, getting those answers in, and rocking and rolling. All right. Hey, I love y'all. Appreciate y'all. Have a phenomenal day and be blessed. Bye.